Welcome back to my channel, and today I'm going to be talking about special relativity. In the year 1905, Albert Einstein published his On the Electrodynamics of Moving Bodies. This was one of the most phenomenal papers that Albert Einstein published in his Annus Mirabilis, namely the Miracle Year. Now, by this time, Albert Einstein had published 4 papers, including the special theory of relativity, which can be also called On the Electrodynamics of Moving Bodies, as Albert Einstein titled his paper. Now, it's important to realize that special relativity cannot just be dedicated to one person. Now, Albert Einstein might be the person who combined it all together, but there were many people before him and after him who shaped this theory. But to understand what special relativity is all about and the proper definition and understanding of special relativity, we must go back in time to meet Galileo. Galileo Galilei is one of the most prominent and influential scientists of his time. Although he created multiple important discoveries that are not recognized all the time, Galileo is still an important scientist and a revolutionary one. It's important to realize that Galileo helped form the foundation for Einstein's special theory of relativity by creating what is now known as Galilean relativity. There is an important concept in Galilean relativity, but in order to understand that, we must talk about a frame of reference. So what is a frame of reference? Now let's consider this analogy. Consider one observer and consider another. Now we have an event happening, and this observer gets a quantitative measurement with respect to their perspective or their frame of reference. And another observer just gets the same quantitative measurement, or a different one, from a different perspective. So as you can see, even though they're describing the same event with the same characteristic, they have different quantitative measurements. The reason is because they're in different frames of references. So frame of reference can just be described in a colloquial term just as a perspective. That's essentially what a frame of reference or a reference frame actually is. It's just how an observer measures everything with respect to some perspective, circumstance, situation, or location, etc. That's what a frame of reference actually is. Now there's another subtle concept that we must get into, and that is an inertial frame of reference. An inertial frame of reference is a frame of reference that is moving at constant velocity, which means it has zero acceleration, or is at rest. This means that the laws of physics, according to Galilean relativity, are the same in all inertial frames of reference. So that means if we have an observer that is moving in an inertial frame of reference, and another observer that is also in an inertial frame of reference, then the laws of physics are the same in both of their frames of references. Now this is an important thing that Galilean relativity theorizes, and it's very important in all of Galilean relativity. Now Galileo just didn't discover Galilean relativity and stop right there. He also popularized the heliocentric model of the solar system, and more importantly, Galileo broke the barrier for mathematics. So what is the barrier for mathematics, and why is it so important? Now, what is the barrier of mathematics in the first place? The barrier of mathematics is that mathematics is what creates nature. Now, although scientists didn't believe this at the time, that's what they truly used. For instance, Nicholas Copernicus' heliocentric model, which we often regard as a very successful model, was indeed correct at describing the heavens, but the geometry that you created and used was wrong when we compared it to the solar system, that the actual heavens actually orbit and actually describe. So it's important to realize that Nicholas Copernicus derived his model using pure geometry, and that geometry didn't work for our solar system, like the orbits of the planets and etc. But his idea and concept that the sun is at the center of the solar system is very important and significant, and that's why it prevailed. Galileo broke this by considering experiments first, nature and observations first, and then applying mathematics effectively. But Galileo was still obligated to do one important thing, and that is use geometry. Algebra was heavily discarded at the time, and geometry was the only source of enlightenment, knowledge, truth, and etc. So Galileo often used geometry to describe everything, and it was successful, but at sometimes it wasn't. So that was a major drawback, because if Galileo had a different branch of mathematics that was often used, then he could have potentially accelerated his discoveries to a huge extent. Galileo also invented many, or more specifically discovered many things about the nature and the universe using geometry, and he did it many times over. For example, he described motion, he described gravity, he described acceleration, and etc. So he described a lot of things that are very important and significant. It's important to realize that Galileo helped break the philosophy of science at the time, as science wasn't even particularly established. But in order to understand what the previous philosophy was and how Galileo truly revolutionized it, we must step back even further in time to the time of Plato and Aristotle. There are two views that we can take at science at the time of Galileo. We can either take Plato's view, or we can either take Aristotle's view. So let's first look at Aristotle's view and then look at Plato's view, as one is a little bit more complicated than the other. Now, Aristotle, as a Greek himself, preferred science, and he did it in an unorthodox way. He believed that truth, reason, and logical deduction were the only ways, or the primary ways, in order to uncover the fundamentals and secrets of the universe. And by doing so, Aristotle did try to account for some of the natural phenomena in nature, but often got it wrong, because truth and logic, yes indeed, they were helpful in doing logical deductions in mathematics, but they weren't particularly helpful in understanding our nature and natural phenomena. So this view that Aristotle carried was a major drawback for him and modern science at the time of Galileo. And this is what they carried until that time, that we can just use truth, logical deduction, and potentially even mathematics to just uncover everything. But Galileo helped revolutionize that. How did he do it? Well, what Galileo did is he essentially just broke that philosophy. He used experimentation. Aristotle used experimentation maybe second. That was maybe his secondary thing. But Galileo used it as his primary thing. Experimentation, observation were the two key and more important things for Galileo in uncovering the secrets of the universe. But for Aristotle, they were the secondary thing. Truth and logic were his primary goals. What about Plato? Plato had a different philosophy in mind. Plato kind of believed in mathematics. The Platonic solids, for instance, are not in this realm. They're in a different realm. They're perfect solids, for instance, as Plato thought of them. Now, what Plato believes is that humans can just use mathematics to describe all of nature. And indeed, even Galileo said mathematics is the language of the universe. But it's important to understand that mathematics is not the creation of the universe. Or in other words, mathematics does not create the universe. Rather, mathematics is embodied in it. Mathematics is not the creation of the universe. The universe didn't create mathematics. Maybe it did, but we don't know that for sure. But we do know that mathematics did not create the universe. So we can't use perfect mathematical objects, perfect mathematical constructions like circles to essentially describe everything in nature, like the orbits of the planets. Rather, we can only use experimentation and observation and pure understanding of our nature and use mathematics with a side to essentially understand our universe and natural phenomena. This is what Galileo did, and this is how we established firmly science, the science that we use today. And science uses mathematics. Indeed, mathematics can be the creation of the universe and nature, but we don't know that for sure. But we do know that one thing mathematics is mathematics do not create the universe. But Plato kind of believed this in a sense, maybe not in a direct sense, but he kind of embodied it. He believed that using perfect mathematical constructions, perfect mathematical ideas, we can essentially embody it in the universe. For example, the planet's orbits must be circular because that's a perfect mathematical shape. And although this logic may seem unorthodox and false, that's what Plato thought was true, or Plato would think that would be true. So it's important to understand that Galileo broke these philosophies with two main important things: experiments and observations. And another thing which he used is mathematics. He used mathematics as a side, but didn't use mathematics as the primary thing to describe the universe. It was experiment and observation. Now that's what Galileo's significance was, and that's how Plato and Aristotle, both really influential Greek scientists, or maybe Greek philosophers more importantly, that's what their philosophies were. And what Galileo did was he contradicted them. He proved them wrong. He proved that experimentation and observation were the two main important things that science should follow. Plato's and Aristotle's philosophies may seem to contradict our intuition today, but luckily we have a new scientist that is potentially even greater than Galileo himself, and that is Isaac Newton. Isaac Newton was one of the most prominent and ingenious scientists of his time, like Galileo. He discovered many things in mathematics and in physics. He invented a whole new branch of mathematics, namely calculus. and he discovered many important and revolutionary things in optics, motion, and gravitation. So Isaac Newton was a very significant and influential individual. But let's consider the lineage of Newton's work. Now, Newton's work have a particular lineage because many people developed them. And we can call this lineage of work Newtonian mechanics. Now, in Newtonian mechanics, there is a concept of adding and subtracting velocities. To understand them, let's consider a car. Now, I'm the observer and I'm at rest on the ground, and I see this big car moving at 10 miles per hour. Inside this big car, there's a little car moving at 5 miles per hour. Now, we don't know about the practicality of this situation, but let's just consider that this situation is actually happening. Well, then to me, the observer, I'm measuring the small car, which is moving at 5 miles per hour inside the big car, which is moving at 10 miles per hour to be 15 miles per hour. I'm saying that the small car moves at 15 miles per hour. I add the velocities of the big car and the small car to get the total velocity that I observe the small car to be moving. Now, what about subtracting velocities? Let's say I'm in another big car, and I'm in the big car driving it. So let's say I'm moving at 10 miles per hour with the big car. But there's another bus. This bus is moving at 35 miles per hour. Now, to me, since I'm moving at 10 miles per hour and the bus is moving at 35 miles per hour, I measured the bus to be moving at 25 miles per hour because I subtract 35 minus 10 to get 25 because I'm moving at 10 miles per hour and the bus is moving at 35 miles per hour. Subtracting 35 minus 10, we get 25 miles per hour. So this is the concept of adding and subtracting velocities in Newtonian mechanics. Now, Albert Einstein comes and finds that there is an important flaw in this method. Now, what is this important flaw? Well, the important flaw is that if we have the speed of light, and the speed of light is the same in all frames of references, regardless if it's an inertial or, let's say, a station or moving frame of reference with, let's say, a positive acceleration. Now, it's important to understand that Einstein, since he found a flaw with this, resolved it in his special theory of relativity. The flaw is that if we have the speed of light as one of our objects, like the car, then the speed of light increases to us, the observer, if it's moving in something else. But this contradicts what we measure because the speed of light is the same in all frames of reference. So that's what Albert Einstein rectified in his special theory of relativity. Isaac Newton created multiple important discoveries, like the universal law of gravitation, which has the equation F is equal to G times M1 times M2 over R squared. And he created F is equal to MA, and so on and so forth. So Isaac Newton was an ingenious scientist and mathematician. Now that we've talked about the forefathers for special relativity, namely Isaac Newton, Galileo Galilei, and Plato Aristotle, we can make this video to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.